Yeah, sure. Up to you, up to you. If you think that's okay. If you want to remove him, I think okay. Depends on you. Depends on you. Okay, maybe. Okay, before we start, I would like you to uh, maybe a reminder for those of you who still hasn't joined the quiz. The link for the quiz, you can check with my last post announcement in the Moodle, the recording yesterday. I put the link for the quiz. So if you haven't joined the quiz yet, you can join through the new link in the yesterday post. You can check. Okay. So any how many of you not joining the quiz? I think one, two. Is there any other? I think should be there. There's another one. But the link, not the same link with the previous one, the different link. You need to open the new link on the new post in my Moodle post, the yesterday recording. Okay. I put the link over there. Okay, and I think some students yesterday after the class they suggest to me for the class notes. Okay, so I think every week I think I can provide every week class notes. Uh, but I will also provide after the whole chapter, so you can look on the notes for every week and for every chapter also. Okay. Okay. Yesterday we discussed the limits at infinity, but I would like to, I think, a little bit review, and giving you some practice. Okay, I hope we can new page. Let me check the. Uh, I think we can check the. I think this one. I think this one. It's pretty much. Uh, I think it's a little bit blurred, but the idea, okay, for if you have any piecewise defined functions and you have or you need to prove the limit, okay, that limit is exists or not, or maybe compute the limit if exists, which means we are going to evaluate each part of this piecewise defined function. And the basic idea for this piecewise is looking at the interval. Okay, that's the very first clue. Okay, because this interval will determine where this function will be. Okay, and by this interval, you can also determine how the value of the limit will be. Okay, so if you want to prove the limit exists or not, check the interval and then check the value, which means you need to go to left limit, the left hand limit, and right hand limit. Okay, so you need to prove that your limit. Let me just write in the concept with a from the right. This should be the same as the left limit, and it should be the same as some value. Okay, so when you have this, which means that the limit is exists. Okay, so the limit as x approaching a is exists and its value is L. Okay, so the same thing applied into our function here, which means this interval is our clue or our maybe we need to investigate this one here. Okay, so when this x less than one, which means it's over the left side of one, we can imagine that it's the x is approaching one from the left, right? So we can make out our limit as x approaching one, right? from the left. Now, the functions will be determined by this piecewise. Okay. So now because it's from the left side, then we are using this x squared plus 1. Okay. Okay. You can directly substitute, right? Remember, the limit, first substitute the limit. That's the first option. Second, if it's rational, you can rationalize. And then you can use trigonometry if it is trigonometry. Okay? There's only, I think, at least 3 options that are very basic. Okay? Now the next one is the right hand limit. Let me write over here. Then this will be 1, which means this is not the same, so it doesn't exist. Okay? Or if you can, well, you can write with another conclusion if you, but we can write uh, since this, you can write maybe g of x is not the same. You can write as a conclusion dne, or you can write doesn't exist. Okay? Okay. And the very same concept, if you want to prove the continuity, before you check the continuous, you can check the limit first, and then check continuity. If the limit doesn't exist, it means that it also doesn't apply to the continuity. Okay? So after you check this, you can check whether it's equal to the function or not. Okay? I think not really complicated. Okay. So uh, my suggestions also, uh, this limit is calculus concept, right? But to understand the functions or how to simplify some equations, you need more of knowledge in algebra. That's different thing. But unfortunately, in our class, in our calculus curriculum, we need to have both. Okay? So you need to have both knowledge in calculus and knowledge in algebra. Okay? Because if you know this, but it is not sufficient. Okay? You need to also know how to simplify the equation. You need to know how the algebra works. Okay? Because if not, then maybe you are only half, okay? Only half knowledge. Okay? So you need to, I believe, more exercise from different sources is it's really helpful. Okay? It's really helpful. Let me check which. Okay, this one. Okay, probably, when you think this limit and then maybe thinking some calculation inside this function here, maybe you'll be distracted or maybe you are getting kind of offended by the questions. But remember, we have a lot of concept, right, in limit, especially if you see any trigonometry like sine or cosine. This is actually one way or one clue that probably we can compare this to maybe some functions, and you can connect this to the squeeze theorem. Okay? So always remember that the sine or cosine, it will have the conditions that is okay. And then it's not over yet. We have e. Then we need to apply E over here. So E with power of something. So E with power of this part, right? So we need to have E as the base. And then this is the power, okay? So we need to just add E, adding E here, here, and here, okay? Okay, and then maybe I can write this become 1 over E, and this become E sine. And what else? We need just to apply the square root of x, okay, to the all these three inequality, these three equations, okay. So we can apply that as well. Uh, maybe a little bit here. And by applying this limit, x approaching 0 from the right, okay. Do you know why from the right? Because of E. E is goes over there, so it ensures that the graph is easily visualized and we can easily describe the graph. Okay? So we can take the limit for all these three, and of course the limit of the left limit here and the right limit is 0. So we could actually look at the answer, and this is going to be 0. Okay, because E is just a number, right? E is just a number, irrational number, a constant. So let's maybe adding the limit. Maybe let me move a little bit. Oh, this question also move. So take the limit. So since maybe let me write with this one. Since is 0, then by squeeze theorem, also 0. Okay, if the question is asked and you need to describe, then you need to describe why this happened by take some word. This is true by this squeeze theorem. Okay. So every necessary steps in calculus, if you need to describe them like in a questions, you need to also describe, let's say, either with equation or with a word, okay, with words. Okay. So every time you have like some complicated one and it has sine or cosine, you need to be careful with that, and maybe you need to check with the squeeze theorem. Okay. And sometimes you need also to see if I have the sine, like for example, if we have this, uh, maybe sine squared x, for example. Now, if we have the square, then we need to careful that it's not -1. So we need to make sure that the left part will be 0 to 1. Okay. As long as we we are sure that 0 is going to be in the part of equation, and we can also can use this in our squeeze theorem. It's also okay if we can make sure that the whole thing is they have connections, okay, all together, the three functions. Okay. We can also have this. Okay. I think I can give you the concept. Which one? Okay, let me just give you limit um, x, because yesterday we applied in infinite. Let's just go to infinity and just take this as example. I already giving the clue here, so you can just continue and you can have some conclusion. So we could use this zero as our equations too. Okay, because we are sure that this sine squared will be in between those two. Okay, so we can use this inequality. So let me write, and let me multiply with 1 over x squared plus 1, and then 1 over x squared plus 1. And we are going to take the limit for all. So since 0 is just a number, so it's just 0, it's constant. The right part, remember the yesterday class? We have x squared plus 1. It's always positive, right? It's always positive function here, the x squared plus 1. So whenever we have the infinity goes inside, we can imagine that plus 1 is insignificant compared with the infinity, right? So it's going to have large number, and we have 1 over a really large number. You can imagine that, and it will goes to approach 0. Remember, this is only applicable on limit. Okay, it's not the same thing if you have some calculation 1 over 0 and you say it's infinity. It's different. Okay, it's a concept. This is 0 because it has this limit. Okay, okay, I hope you get my point. So since limit then limit also 0. Okay, and then after all this part from I think some of our feedback quiz, okay, I will I would like to also discuss the I think a few homework, okay, a few homework problem um, that I want to emphasize. I think some of students asking I think the last question, I think 2 or 3 asking me, and maybe one student maybe not completed the last one. and another student's having difficulty uh, to complete the last problem. The last problem is I think I will go to the next page, okay, if you don't mind. Huh? This one? Or do you want Zoom or this one, right? This one? Maybe a little bit Zoom. Okay. Okay. Anyone clear? Okay. Okay. The last question in the homework is if the limit first is you need to find this. Let me start one by one from here because the idea is it's the same. The two questions the same idea. So you have the conditions that state your limit as x approaching 0 of functions. We are not sure what functions that is, but that functions define the x squared. They are all equal into 5. So based on what we have, we are going to use some assumptions, and we are going to have all the assumptions that obvious and then easy to follow. And then let's just say that we can say that if we want to apply this into our this just f of x, okay, although we are not sure what kind of function that is, we can apply that uh, remember when you have limit, what is the first thing you are going to do? You check the substitute the x into the functions, right? When we substitute, the first thing that comes into mind is we have 0 on the denominator. Okay, so let me give you some chart. Okay, what could happen? The logic thinking, what could happen with limit? So you have a limit. Let's say a. First thing is substitute, right? After we substitute, what's going to happen? It has several options or several conclusions. The first thing when we substitute, well, we get a value, which means the limit we can compute easily, and that is the result of the limit. Okay, so the value. The second, maybe we are going to have, well, maybe it's a 0, so it's also a value. So okay, that's we finish. Or we are going to get what we call 0 over 0. We call this indeterminate form. Remember in the previous section that I mentioned about this 0 over 0, what we can do is we can simplify it, we can rationalize, we can use trigonometric identity if we have. Okay, so all those things, so we can simplify it. First is factor out or factorize, and then what else? Rationalize, and then if it's trigonometric, we can use the trigonometric identity. Okay. Now, if we are following these steps, eventually we are going to get some result. Okay. Now, this is the logic or the reasons. Okay. Why? For our questions, because it has the result 5, but it has the denominator 0. So we are going to have at least maybe it's 0 over 0, and we are going to do something about maybe we need to have rationalize. We need to multiply with something, okay? And for other question as well that has that typical standard like this. This is the logic thinking that you need to follow. Okay? So when we have this, okay, so this perhaps going to be 0, right? It's going to be 0. So we could actually conclude from those logic thinking, you could say this is going to be 0, but we can also use some calculations here. Okay, how about we implement this? It's okay, right? It's okay. It's not a problem. And then we are going to just limit all this. And this will be going over here. And we are also going to limit the other part as well. So since the left part is 5 and this x squared 0, okay, it's also 0. Okay, not a problem. The same result as our logical reasoning. It's also 0. Okay, because there will be some variations for this type of question that you need to follow. That like imagine that if you put the functions or if you put the x into the functions, and if the result either top or denominator is 0, it has some number. Maybe it's 0 over 0. That's one assumption. 0 over 0, one assumption that you can think. Okay. So the other questions, we can follow the same concept and also follow the same computations. Okay, this is what's going on inside, okay, in the process. So when we have the other part, it's asking over x like that. We can also think that, okay, let's just multiply with x over x. So then one part of this limit will have the same with the information that is x squared. And then this part, the right side is just x. And we know that the right part is 0, and whenever we multiply with 0, the random result will be 0. Okay. So this is 5, this is 0. Okay. So I will give you the answer key for homework later, and also answer key for the quiz, maybe next week, okay, for the quiz, because some of you still have a quiz this week. By the way, the link for the quiz, the new link, it will only last until I think tomorrow night. Tomorrow night, so you need to click the link as soon as possible. Okay, if you haven't joined the quiz. And also, if you maybe having exercise some questions and have some trouble and you would like to maybe discuss with me, you can take the photos or maybe screenshot your problem, send to my email, so I can read out and maybe give you some tips or notes. Okay, you can always do that. Okay, I think students from previous years they are also doing this, and I think that's okay. I think one student who are discussing with me through Moodle, asking me this one. You're right. Yeah, yeah. I think it will be okay. You can email and then take picture, because in Moodle I think not really easy to send the picture. I think email better. Yeah. If you want to like discuss more detail. Okay. And if you feel your English not really good, I think just a screenshot of the picture and then use any Um, Even you can use Chinese if you want. Well, I will just use translation. But I will know from your picture. I will know from your picture. Okay. So the picture is really important. If you want to know like the really details, okay, the picture is important. Okay. So the important thing, the picture. Okay. Okay. I think for just a little review, I think I will stop here, and we are going to continue. As I mentioned, we skipped some part on 2.6. That will be in additional notes I will add later. So we are just continue to 2.7 in the textbook. That is going to be the derivatives, okay? The introduction to derivatives. So we are going to explain from limit what can we do for derivative, or how derivatives comes, okay? How and where does it come from, okay? So this is the intro to derivatives. And I believe some of the derivatives, like if you have a functions x squared, you derive becomes 2x, you already know about that. And you are practically compute all your mathematics problem as easy like that for some derivatives, right? But what I want to tell you in the beginning here for the introduction is why and how. Okay, why and how. Okay, so we are going to start from the limit. Okay, we are going to start from the limit. So remember that we have, I just make a random, maybe not really, maybe like that. Let's say this is a curve f of x. Okay. And if we take 2 points, let's say this and maybe here, let's say this is A, and the second one, let me just use x as variable. Okay. Now the idea is this point Q, I can move freely, so this x can be moved also. Okay, we can move this x, so this Q will be have different point on the curve. Okay. Now to begin with, I will take the line connecting P and Q. Okay, that is the first thing I need to do now. So let me take this line. This line is called the secant line. Okay, the secant line. Secant line. Let me write. This is the secant line. Okay. And if you learn about physics, then if you learn about the kinematics, you have the velocity, distance, time, right? If you imagine this like a time and distance, this secant line is your average velocity. So this is distance and time, if you imagine like that, if you remember your physics. So this is the average velocity. As we also mentioned, I think in the previous sections, when we have the limit concept, and then we have also the concept when we have a ball, and then we are having we not throwing the ball, but just let off the ball, and then we need to know the average velocity after some times, but it's not giving you the exact interval. So we are going assuming the interval from 0.1, 0.01, and so on. And from there we can also get the limit concept, right? And similarly, okay, from here, what we are going to do is this secant line. Okay, since this point Q we can move freely, the idea is, or let me write the secant line first, okay, before getting those idea. So the secant line is basically this triangle. The triangle from this, okay. So uh, P is A, f of A. Okay, I hope you can adjust your notes. Okay, sorry if I add more more variables, but I hope you can adjust your notes. So the secant line becomes, let's just make this as m, the gradient or the slope between P and Q, or before the long one, we can just telling this become the difference between y and x, and this becomes f of x minus f of a, and then divided by x minus a. Now from this m, that's the secant line, or if you think in physics, that's the average velocity. Now this point Q, we can move freely, so you can imagine it can be in anywhere in this curve. Now imagine this Q is getting closer, closer, closer to this point P. Okay, it's getting closer, and we know from the very concept of limit that the getting closer concept is the limit. So when we have the secant line, you can imagine how the secant line will look like when it's going to be closer to this point P. So from here, so if you see my hand here, you can see if this is here, maybe it's going here, and eventually when it's getting closer and closer to P, is getting close to the tangent line. Okay, the tangent line means the line that is tangible to this point P, which means it's getting in touch the point, only one point directly in this point P. Okay, so let me draw a little bit. Sorry if you take some notes here. Okay, let me use maybe green. Maybe this is getting closer. Okay. And this is what you call the tangent line. And from this tangent line concept, we can have at least 3 or 4 subsections in later calculus. Okay? Either for approximations, either from the theorem, we can have a lot of concept from just this tangent line. Okay? Okay, of course, if you see, maybe if you imagine this line really, really thin, because this has a pixels limitation, so you can see that it seems to see the same, but eventually the same is, if you see the curve, the blue curve and the green line, when you close this or you zoom in this P, you will see that the tangent line and the curve is getting closer and closer, and it seems that at the point that is close to P, the curve is behave like a tangent line. The curve, it's like a straight line. It's not quite a straight line, but it's similar to straight line. Okay. So that is one way we can approximate something. Okay? One way we can have that. I think in the next sections about approximations. So because we are getting close, then we can also have definitions. As I mentioned, the tangent line. Let me write the tangent line to the curve y equal f of x at point P, A, f of a is the line through P with slope m is the limit as x approaching a. Okay, that is precisely what we are doing. We are getting close the point T to point B, so x getting close to a, and then we are going to have this secant formula here. Okay. If you would like to see the visuals, I think you can also check this. This is, I think, more clear for the picture. So the point Q is getting closer. You see the second line getting closer to, and then after it goes to this P, it's getting closer to this tangent line. So we can say the tangent line is the limit of the secant line actually. Okay. And for now, this slope, you can say it's like your first interaction with the uh, the we are not saying it's derivative yet, but it's supposed to be the derivative. It's supposed to be the derivative, but later we will going to see. Okay, before going to derivative, there is uh, another way to write down the formula. Okay, so this is one way to rewrite. There is another way. Okay, okay, let me put the which one? This one. Yeah. Okay, another way. It's actually the same thing. It's actually the same thing with the this one. We have ax, right? Another another way is we are going to have a and then a plus h. Now what we are going to do now is we are having the distance h. Okay. Now instead letting this point closer here, we are going to have this h getting 0. Okay. So what we are going to write is that m is the limit as h getting 0. Okay. Now the second line is still the same. It's going to be this delta y over delta x. The delta y, according to what we have, a plus h, so f of a plus h minus this f of a, so this distance, over h. So we are going to write also that. We can also imagine, as I mentioned before, the average velocity. So average velocity, remember this is distance or displacement over time. If we imagine the h is being a time, then the displacement is the function itself. So we are going to have f a plus h minus f of a over h. We can imagine this being a physics problem. So the m, if we say we have average velocity, then the m is our instantaneous velocity. Okay, so we are going to have instantaneous velocity, or let me write VA limit. Well, it's actually the same thing, but we can use the physics to approach this. And of course, all the assumptions you need to provide the limit is exists. Okay, that's important. If not exist, then it will be wasted. Okay, now what is our conclusion from all the points that we mentioned about the limit? Well, if you think on the picture, whenever you have a conditions that is have something to do with change, see that this is having to do with change, right? It's getting closer to here, and we say that, okay, we have this as our limit concept. So whenever we have something that has change and we know the rate of change, as for example, we have the velocity and we have the instantaneous velocity, well, for all problems that has the rate of change, we need to have another simplified concept to call that whole part, right? And that's why we have, and that's the concept of derivative. So everything that has rate of change, we can write as derivative. Okay. So if we have something to do with, like, I think velocity is easy to visualize. So when we have something that, okay, we have movement, we have velocity, and we know that in some part we know the average velocity, but we also do know from the limit the instantaneous velocity, like exactly precisely when you move at t equals some seconds, you know, oh, how fast you are, the instantaneous velocity. And that's how the limit works. And from there, we know for every point, we can actually figure out how how instantaneous velocity are. Okay. Okay. So because it's worked from for every point, it works for every point. So we can say that the concept of derivatives. Okay, let me write here as a conclusion here. So whenever we calculate uh, concept concept rate of change, the formula m equal, or maybe not m, maybe just limit h goes to 0, we can say arise. Okay, arise means we are going to see every time we have rate of change, we are going to see this. Okay. Now we need just to take this as our definition. So I think I need to go to the next page, but you can write first the notes, or maybe taking break. Okay, taking break. Okay. You feel okay? You feel okay? So your COVID okay? Do you feel any symptom with COVID or no no symptoms or just normal? Any I mean any difficulty when you have COVID? No? Oh, okay. Okay. Let's go back to to calculus again. Okay. We come back from your dream to reality. Okay. Okay, so the conclusions, because we have this limit form appearing in most of the rate of change cases, then we are going to have some definitions. Okay. So definition. So the derivative. So let me just describe as the derivative of a function f at a number a denoted or symbolized by or denoted by f, and with some accent, we sometimes call this f prime or f accent, or you can just call the first derivative of f at a. So this is equal to f prime a equal limit sh approaching 0 and f a plus h minus f of a divided by h. Of course, if limit exists. Okay. So that's the conclusions from what we have before. Okay. And also the same thing with the other forms. We have another forms, right? We can also write And to connect this, we can imagine that the x is the distance from A after plussing the h. Or we can say the h is x minus A. So when h approaching 0, then x approaching A. So these two will be the backbone of derivative concept. So this is the first step, entering the derivative. So actually all the uh, derivatives formula you maybe have learned before, it came from this. So when you say x squared, you derive becomes 2x. It actually came from this. Okay? We can actually try how to do that. So x squared become 2x is a conclusion. Okay, it's a conclusion. The process is actually using the limit. Okay, so if we have, yeah, let me just give you a polynomial like that. If we want to evaluate the derivative at number 2, then actually we are going to use the limit process. Okay, let's just try the whole process first, and then the conclusion will be very easy. Okay. Limit. Let's just take the h. So this will be divided by h, and then this will be f, and then 2 plus h. So we could check the f of 2. Um, 4 minus 16 negative 12 plus 9 is negative 3, right? So by doing this means we are going to uh, check all the value into the functions. Okay, let's just take this old ways, okay, just to see the proof. So 2 plus h squared minus 8, 2 plus h plus 9 minus 3 divided by h. Okay, still, let me give another line. This will be 4 plus 4h plus h squared minus 16 minus h 8h plus 12. too long. And you will see negative 16 with 4 and 12 will cancel all together, become 0. So we will have 4h minus 8h is negative 4h. So maybe I'll write here. Limit is h squared minus 4h divided by h. So this will be limit. So eventually you have the h cancels out. And as limit getting 0, we plug in here. Then we get the result is negative 4. Well, this is, we calculated the numbers directly, evaluated at the point directly. But we can actually, we can imagine this being a function. So it's not, maybe not 2, but maybe another variable, maybe x. That's also possible. I will write maybe later, okay? But this just to remind you. But from what we have here, we are able to actually using this limit as a means to derive, as a derivatives tool. So when we derive something, this is what actually happened inside your derivatives. Okay, so it's not like a magic, like 2x squared becomes 2x. It's not magic. It's limit. Okay, in the inside process. Okay? Sometimes because we are so familiar with the derivative, we forgot about this. Okay? But this is actually the very core concept of derivative. Okay. Okay. Uh, okay. Another concept, because we already talked about the tangent line. So another concept or another typical problems that might be asked is finding the tangent line, the equation of the line. Okay. The linear equation. Okay. So let me give you the background first. So for now until maybe next week, we are going to have more concept on derivatives. Okay, at least the introductions, and how we are actually looking the graphs, and maybe take times to differentiate, not differentiate, to observe the different from the just a function and the derivative of the function. Okay, that will be next week. Okay, so let me just give you the tangent line. Tangent line to curve. I'll maybe make a little bit bigger. To curve y equal f of x at point P. It can be any point. Is the line that passes through P and has the slope m. Which means, because we have the slope m, we can also say that is equal to f prime a. Or we call this the derivative, first derivative of f at a. So we can say that this slope m is actually equaling to this f prime of a. As a conclusion, remember that the point P is a f of a. Then if you write the linear equation, okay, we can rewrite them as y minus f of a equal f prime a, and then x minus a. So to find the line equation, at least you need the slope and the point. Okay? The points f of a and a. You will see a pattern from this, okay, later on. So keep in mind of this tangent line equation. Okay? We are going to see how we connect this to some theorem in calculus, okay, some theorem in calculus, and also applications in graphics, okay, from this theorem. Okay. So this is the line equation. Okay. Tangent line, or we can say tangent line equation. I think to make it more simplified, I think you can also relate to just a simple line equations. I think that's pretty simple if you want to think that way. Um, okay. Okay, just a simple line equations as usual in the linear equation. What you need to do is just replacing all with the new concept with the derivative one. And I think this tangent line, it becomes like a typical questions that usually asked in exam. Okay. Well, of course, it's not maybe not only asking like line, but it will be having this concept, okay? The same concept. All right. Okay. Now, as I mentioned, the derivative, we can also treat the derivative as the function itself. Okay. So we have a f of x. Before we only categorize using the a, right? The point a. Well, actually, we can just take a and replace with just variable x. And that's still okay. We can treat the derivative as a usual function. So we can have a function and we can have a derivative of that functions in general. Okay, not only at specific points. Okay, that is the way that you did. Like x squared becomes 2x. That is the way we did, right? It's another functions, right? Okay, okay. Let me just write just a quick note here. So if you have, let me write. Usually we have A as our observations point. We can replace become X. So we can say this is a derivative as a function. There are some examples for the tangent line, but I will skip that for now. We'll focus on the concept first. And the tangent line will be very simple if we know how to derive, right? Okay. So I will skip some parts for now. Okay. Now, okay, to begin this concept, derivative as a function, we need to at least visualize how it looks like. So perhaps giving you uh, some graphs. Which one is no graphs? Is this the graphs? Okay. Okay, now we have this, let's say this is a random function. We're not sure what function this is, but we know this is f of x. Well, it asks to, how about the derivative of this f? Okay. Can we roughly sketch from this? How? Tangent line? The slope, right? The slope, right? Okay. So the idea is using the slope. Okay. First is you see it's going down. It tends to have the slope negative, right? And when it goes here, how about the slope? 0. Okay. And go here, it's positive, and then 0, and then negative. Okay. At least that is one clue. Okay, one clue. And to connect with the new graph that we are going to write, then we can start with 0. We can start with 0, which means that f prime, the slope, is 0. If we have y equal f prime, then we are just taking which one that has 0, that crossing the line. Okay, so we can take, so let me make some notes here that this will be m is 0, right? This also 0. And then what else? Yeah, I think these two first, okay? And then if we want to make maybe another curve that here. Okay. Okay, we would like to write down the f prime x. Okay. Or maybe let me add, this is m is negative. Let me just write that. M is positive, m is negative. Okay, just to show you the slope signs. Okay. Now we would like to draw this. Okay. We know there is 0, the slope is 0 is around this 0 and 1, but I don't know where, but let me just take line going down. So let's take this and take the point here, which means the function will cross this, right? Because it's 0. Okay? And then another one is around here, right? Let me just take line and make the connection. Because we are not sure what function this is. This is just a roughly sketch. Okay? As long as it is consistent with this slope, right? So another one is here. So at least we know these 2 points. Okay? Okay, now the next step, we know this is negative. We have f prime here. Which one is negative? Is it here or here? Which one is negative? Okay, maybe giving you a number. Giving you a number. So 1, 2, -1. Okay, which one is negative? Downside, right? Maybe let me make a little bit longer. Okay, make it a little bit long. Now I'm not sure how long we need to have the function, but we are sure that this should be the slope negative, and this will determine the slope itself in terms of our f prime, a new function. So we are going to have some line, maybe the curve around here, and then, well, maybe it goes maybe going here, and it's crossing through. At least roughly we have that that behavior for the graph. So we are going to have. So maybe it goes. Well, we are not sure how well. Maybe just that, or maybe just line, not really straight, or maybe a little bit straight. Again, we are not sure how it's going. But then it appears, okay, at this interval we have going up, okay? We have going up. But for a clue, because this is in different chapters, the next 2 chapters actually. But let me just give you a clue. Okay? If we zoom in here, okay. Imagine the slope is changing from this 0 to another 0 here. Okay, it's plus. Okay, it goes plus, but let's see how the plus will be. It's plus, okay. But then at this point, okay, if I draw for you here, maybe here, okay, here. Maybe after this point, it's actually going down, but still plus. Do you get my idea? Okay. So it will going reduce again up until 0, which means this part here will be its maximum point. Do you get the idea? Okay. Actually, we can prove this later with the second derivative, but it's not yet that chapter. But this is just an introduction. But we know that this going to be well around this. I don't know where, and we are not really care much for that point. We just roughly sketch. Okay, so perhaps this will be maybe going here. Well, I'm not sure how high will be, but let's just say that's the maximum, right? The maximum value, and it's going down, right? And it's going to be 0. And then the same thing will appear here. It's going to be our minimum. So we will have, and then the same thing apply. Okay, the same thing apply. So we are going to have, And then we maybe stop there. We are just focused here, and we can just to make sure, negative, positive, negative. It's exactly as the slope in the original function says. Okay, so it's negative. Oh, why it's positive? It's negative, positive, and negative. Okay. Okay. I think because the next step is actually telling on the differentiability and some example of how to see a function and it derive it and become another function. We are going to have that in next week. Okay, that's okay. That's actually the time that I will end up under here. Good timing. Good timing. Good timing. Okay. We are going to have again the feedback quiz. Okay. But that will be the concept from the limits and at infinity. Okay. I hope you still remember. You can open your notes if you want. So actually, in your textbook, they begin to have like example with using the limit. But for me, I think just a few example for the introduction, and then more example at the I think after we have all the concepts, because I think it will be really easy because you already know, and some of you familiar with the derivative, right? So I think we just go through some concept first and make sure we are on the same page, and we can have I think at the middle or maybe at the end more practice to have more practicality in the derivative. Okay? Because after this there will be a lot of techniques that, like I said in the beginning, if your algebra may be not sufficient, you need to have more practice. Because calculus, it's not just calculus, it also has to be algebra. Okay, let's join. This will be limit part 4. I think we will have limit part 5. So the derivative, the introduction, it's still on limit. Okay, it's still on limit. Still on limit. It's derivative, but it's still on limit in the chapters. The chapter is still on limit. Still on limit. Okay, then we can start. We can start and use your, I think, student ID. I'm not sure if I think I can check from here before we start, just to make sure I add a correct timing. If not, then it will be very, very fast. Okay, it's okay. Okay, I hope the time is okay. Okay, let's go for the first one. So it's too small if you see from here. You can see in your screen. I hope 2 minutes, okay? 2 minutes, okay? Remember the notes on the yesterday's class, the limits at infinity, what you need to do, and I think if you get the clue directly, you can get the answers also directly. Okay? Be careful on the power, okay? The negative power. upload easily, right? Yeah, yeah, I think it's easily because the you can cancel. Why is it answering yes? Why? Okay, okay, okay. Okay. Okay, okay. Oh, okay, okay. Okay, I only have one more question that you can have. We already discussed, I think, in the beginning of the class. Yeah, I think 30 students, 16 already. So I think 1 minute. I think enough for me. I give too much. Yeah, yeah, yeah. Yeah, ready for 36 students. Who's still writing? Who's still writing?
I just
Yeah, 6, 5. Okay. Okay, good, very good, very good. Wow. Ready? in the wind.
Oh,
21, push 21. Okay, okay.
okay. Good. Good. Okay, as usual.
Write your ID and
Yeah, we are early 10 minutes. Yeah. Okay.
if you have any questions, we can discuss with me. If not, then you can go to your next class if you have. See you next week.